Hi everybody, welcome back to Super Awesome Calculus. We're in Chapter 5 entitled The Fundamental Theorem, and today we're going to go over the concept of the definite integral. Now last time, as you may remember, we talked about the notion of finding the area under a curve or finding a distance, finite distance given various speed intervals. And that kind of, I ended this by giving you a question, and the question was, the speed of a runner increased steadily during the first 3 seconds of a race. Her speed at half-second intervals is given in the table. Find the lower and upper estimates for the distance that she traveled during these 3 seconds. Now, I mentioned to you before about using right and left endpoints. I get my right and left mixed up all the time. I generally use right-hand endpoints, because if you don't use right-hand endpoints, you're going to be not computing v sub t, or vt at a certain time. It's going to be v at the time minus 1. So for instance, instead of starting at the first second, you're going to start at 0 if you use the left-hand endpoint, which makes a lot of sense actually. You're either starting at the half-second right-hand interval or left-hand left interval. Left-hand starting at the left side will give you a lower approximation. Starting at the right-hand side will give you a higher approximation. So let's write this out. Well, here's time, here's velocity. Time is in seconds, velocity is in feet per second. Well, time, we've got 0, you got a half, 1, 1.5, 2, 2.5, 3. Oof. I just got it in there. That's what she said. Anyway, there we go. Okay, the velocity is 0, 6.2, 10.8, 14.9, 18.1, 19.4, and 20.2. Okay, you probably got this because I gave that much to you. What I'm basically saying here is we want to find v of t, a function, velocity with respect to time. V of t, we know v of t is increasing because the speed is increasing over the interval, increasing on the closed interval 0 to 3. Now I mentioned that you can find this by taking a sum, a Riemann sum, r, how many intervals here? R sub n, but we know what n is. We've got 1, 2, 3, 4, 5, 6, so between 0 and a half, between half and 1, between 1.5, we've got 6 intervals here. We've got 7 entries, but only 6 intervals. So R sub 6. Now, I mentioned that this is basically like saying the sigma, with the n being 6 and I equaling 1, of v of t sub 1 delta t, or v of t, yeah, delta t. Now, what this means is that we're going to take all of these values and we're going to add them together. So what's delta t? Well, delta t is the change in the interval, or how long is each interval. In this case, each interval between 0 and a half to 1, 1 to a half, it's pretty easy to see that delta t is 0.5. And I'm going to add, or I'm going to multiply that 0.5 times the sum of v at a half a second, plus v at a second, plus v at 1.5 seconds, plus v at 2, plus v at 2.5, plus v at 3. But I know what those are. I know what those values are. They are 0.5 times 6.2 plus 10.8 plus 14.9 plus 18.1 plus 19.4 plus 20.2. Okay? And if I add all of these up, I'll get 89.6. And then I'll multiply that by a half, this half right out here, and I'll get an upper estimate of 44.8 feet. Okay? You with me? Good. Well, that's the upper estimate. If I want the lower estimate, I'm still asking for a Riemann sum here. I'm still going R of 6, but this time we're still going from 1 to 6. But instead of V, so V of t, it's going to be V of t sub 1 minus 1 times delta t. This is why I don't like to use left-hand limits. Tend to get hung up there. And that's going to be 0.5 times the left hand, which is 0 plus 6.2 plus 10.8 plus 14.9 plus 18.1 plus 19.4. Notice we stop at 19.4 because that's the left endpoint of the interval between 2.5 to 3. So that's what the value was at 2.5, 19.4, so that's where we're going to stop. Adding all of these together gives us a half times 69.4 for a total of 34.7 feet. So those are the upper and lower estimations. Now, building off that idea, you should be fairly familiar with what we talked about last time when I mentioned that this sum right here, that this limit, the limit as n approaches infinity, if we split up an area under a curve into an infinite number of rectangles, we'd write that as such, f of x, little star up there, so 1 delta x plus f x star up there, 2 delta x plus dot 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 plus that dot dot dot, that ellipse means however many you want. It doesn't really matter, it's arbitrary. X star n delta x. That sum, that big long sum, is the same as the limit as n approaches infinity of the sum from 1 to n, I equals 1 to n, of f x star I delta x. Well, now, to introduce the idea of the integral, we're going to take this a step farther. And we're going to say that if f is a function, if you have a function that's defined between a and b, in other words, as long as this is not one of those step functions or discontinuity, if it's defined between a and b, we'll divide that interval into n subintervals, n rectangles, of equal width, delta x, same width. You know, we're just saying that if it's continuous, we're going to split this into a and b with n subintervals, all of the width delta x, and delta x equals b minus a over n, which makes sense. That's definition there. I mean, it's intuitive. We let x sub 0 equal a, and x sub n equal b. And those are the endpoints. And these x stars are any sample points. In other words, if this is 1 over n, 2 over n, 3 over n, b, that's a sample point, that's a sample point, and that's a sample point. Sample, sample, sample. That's what these x stars are. That's what we did last time. We will then say that the definite integral from a to b, in other words, this thing, we're going to write that in a special way. And this is notation we'll be using from here on out. This funny little s thing, Leibniz made up, from a to b, f of x dx. That is what an integral looks like. Now, this isn't really a product. You shouldn't really think of it that way. I mean, you can, but it'd mess you up. So basically, dx is just there. It tells you that the independent variable that we're going to be using, that we're going to be integrating, is x. If it were dy, we'd be integrating y, but we're not. We're using x. So there you go. That's what an integral looks like. This is the same thing. It's telling us to do the same thing as that. I'm going to sneeze. I'm allergic to Florida. Anyway, there you go. So, let's see. That's the definite integral. Okay. A couple theorems that I'm just going to read, and I'll try to put them into understandable terms if they're not immediately accessible. If f is continuous on a to b, or if f has only a finite number of jump discontinuities, then f is integrable on ab, that is, the definite integral exists. In other words, if f is continuous on AB, it's integrable. If it has a finite number of jump discontinuities, in other words, if it goes from there to there, but then picks up here, one jump discontinuity, that might be integrable. In fact, it will be integrable. If you'll find that another discontinuity would be if it's discontinuous at B, well, in some circumstances, but we're not going to get into improper integrals yet. So basically, most functions that we're going to be looking at are going to be integrable. Here's an important one. If f is integrable, int period is how I'm going to abbreviate that, on AB, closed interval, then a to b f of x dx equals the limit that we talked about, the Riemann sum limit, from n, I equals 1, f of xi, or x1 delta x, where delta x is b minus a over n, and x sub I equals a plus I delta x. I basically just said that, but there it is formally. Now, I have a choice here. I'm looking at the time. I don't really know if I have the time to do this or explain this too well. Yeah. Now I'm wasting that time. So, okay, screw it. I'm going to do it. All right. I'm going to rush through this. Watch, follow along if you can. You don't need to, but this might help you understand something. Okay, first, you need to remember a couple formulas. These are all from n, I equals 1. So to n, I equals 1. To n, I equals 1. Important things. I squared, I cubed. You might remember these formulas from algebra class. N times n plus 1 over 2. N times n plus 1 times n plus 2 over 6. And n times n plus 1 over 2 squared. When you encounter an I, you'll use this. That's what I equals. And I squared equals this. I cubed equals this. Note, that I is index. It's not the imaginary unit. Now, other important things you'll need to know. You might want to know. From here on out, if I just write a sigma, it should be understood that's from I equals 1 to n. So sigma C is NC. Sigma C a sub I is C sigma a sub I. Constant multiplied times the sum. The sum a sub I plus b sub I is the same as the sum of a sub I plus the sum of b sub I, and the same is true, I did, for a sub I minus b sub I. It should follow. So, with that, I'm going to show you how to compute the sum for this function right here. Follow along if you can. F of x equals x cubed minus 6x. And we're going to take sample points to be the right endpoints. A equals 0, B equals 3, N equals 6. 6 rectangles between 0 and 3. So we know that this is going to be delta x equals b minus a, 3 minus 0 over 6. Delta x is 1/2. All right, great. So we know that. So what we're basically saying here is this Riemann sum from 0 to 3 is going to be f using right-hand endpoints. So we're going to use, if we break it up a half each time, we're not going to start with 0, we're going to start with f at a half. F point half plus f of 1 plus f of 1.5 plus f of 2 plus f 2.5. We could go up to 3, yeah, plus f of 3. You're going to multiply that times delta x. So that's going to give us 1/2 times negative 2.875 minus 5 minus 4 plus 0.625 plus 9 equals negative 3.9375. Okay, great. Now, if you were to graph this, you'd be wondering, how can the area be negative? Well, if you'd graph it, you'd see a larger portion of the graph is confined to the negative side as opposed to the positive side. So that's an area. Now, in general, if we're going to, that's the answer we get for that part. But we remember that f of x equals x cubed minus 6x. A equals 0, b equals 3, n equals 6. If we're looking at the integral 0 to 3 of x cubed minus 6x dx, well, then we have to write this as a Riemann sum, which is the limit as n approaches infinity, n I equals 1, f of xi delta x. Okay, so let's plug in what we know from here into the Riemann sum. Well, that means that we know that we're looking for the limit as n approaches infinity from n, I equals 1, 3i over n, over 3n. We have, right? Yes. Because x0 is going to be 0. Am I confusing myself here? No, because we have 3 units, we're just going to compute 3 over n. 3i over n is what we'd get if we plugged in the function. So, using the laws that we just went over, this limit is 3n times 3i sub n cubed minus 6, 3i over n. I really don't want to go through the rest of this because I only have 8 more minutes. It's not really worth it, I don't think, for right now to see how this works. But basically, if you use that I cubed definition that I told you about, and the regular I definition, you'll end up getting 81 over 4 for there, minus 27, which is going to equal negative 27 fourths, which is going to equal negative 6.75. So that turned out to be a colossal waste of time. I apologize, but I wanted to at least attempt it. So, on to more important things. All this right-hand endpoint, left-hand endpoint thing is just a problem. So let's make this a lot simpler by introducing a rule that'll make this a lot easier. It's called the midpoint rule. And it basically says that if we have this integral, a to b, f of x dx, it's going to be approximately equal to the Riemann sum of x sub I midpoint delta x. In other words, instead of picking, for instance, if we have 0 to 0.5 to 1 to 1.5 to 2, instead of picking 0 or 0.5, we'll pick the middle. 0.25, 0.75, 1.25, 1.75. And we'll just pick the midpoints of each one. And the midpoint will be our left-hand, right-hand endpoint, and we'll just keep it at that. Now, basically the midpoint rule says don't pick right hand, don't pick left hand, pick the middle, and the integral is going to be basically equal to that. It's going to be approximately equal. And if delta x is sufficiently small, it'll be very, very close. So basically, if we have the integral 1 over 2 of 1 over x dx, n equals 5, well, we know that we've got 1, 1.2, 1.4, 1.6, 1.8, 2. 1, 2, 3, 4, 5. We're not going to use 1 or 1.2. We're going to use the midpoint, 1.1. So it's going to be 1/5 b sub a, b, a, 2 minus 1 over 5 is 1/5, times 1 over 1.1 plus 1 over 1.3 plus 1 over 1.5 plus 1 over 1.7 plus 1 over 1.9. And when we add all these up and multiply times a fifth, we're going to get something like 0.069, which is going to be very close to an important number. But anyway, there you go. That's the idea of the midpoint rule. Now, some things about a definite integral that you might want to know. I'm working to get this done. Oh no. We're going to have to leave off the comparison properties of the integral. Okay. If we have a to b, f of x dx is equal to negative, b to a, if we have b to a, that's equal to negative a to b fx dx. This one will be important. From a to a, the integral between the same area, I mean that's obviously the area of 0. What's that area between nothing and nothing? It's 0. If you have a constant, you can multiply the constant times the integral, just like with derivatives. The sum, the integral of the sum f of x plus g of x dx is the sum of the individual integrals. Same with the difference. Went over the constant. Yeah, great. Also, the integral of a constant, a to b, is c times b minus a. That's something you'll see an explicit reason why next time. Also, if you have piecewise, or not piecewise, but yeah, piecewise integrals. For instance, let's say we have from a to c of f of x plus c to b of f of x dx. Well, that's the same as from a to b f of x dx. In other words, you're just splitting the area in half and adding them together. Okay. Comparison properties. I'm just going to read them. If f of x is greater than or equal to 0 for x being between a and b, then the integral is going to be greater than 0. If f of x is greater than g of x, and x is between a and b, then the integral of f of x is going to be bigger than the integral of g of x. Makes sense. And if if f of x is between the minimum and maximum of a and b, then the minimum of that the minimum number of b minus a is going to be less than the integral of that function, which is still going to be less than the maximum. times b minus a, less than or equal to. So those are comparison properties. Now, that's the end of this lecture. I'm almost out of time. So, final big problem I leave you with, I promise these last two lectures have been sloppy. The next several should be much easier. This was really convoluted stuff. Use the form of the definition of the integral given to evaluate the integral between 1 and 2 of x cubed dx. If you can't do it quite right, don't worry about it. I'll try to run through it next time. And next time when we finally learn the fundamental theorem, that function is going to be super easy to integrate. All right. Thank you very much and take care.